So when we shoot a projectile here on Earth, we also get a curved path, right? This whole time I've got an arrow or a ball or a bullet or whatever it is that I'm shooting into the air. Whatever, that object is going to be following a path that looks like this. It will be moving. If it has a velocity in the y direction, up and down, it'll be moving up as a result. But the entire time it's in the air, gravity is going to be pulling it down towards the Earth. And because it's accelerating, the velocity it gets is going to be higher and higher and higher as it reaches towards the ground. So its position is going to take the shape of a curved line, very similar to what we looked at last time with our position versus time graphs. So in other words, a curved line, a curved path will show you acceleration. So projectiles will have curved paths that curve towards the Earth as a result of the acceleration of gravity, the force of gravity pointing down, lowercase g. Okay, so let's go ahead and examine the motion of a projectile in our next example problem. Here we've got a cannonball fired from a cannon atop a 7.4 meter hill. The muzzle is tilted 26 degrees above the horizontal. The cannonball's muzzle velocity is 24 meters per second. Please give x and y components of the cannonball's velocity and acceleration at each of the following times. Okay, so here what I'd like you guys to do is split your velocity into x and y components and determine what that velocity of the cannonball will be at each of these times, in the x and in the y direction, please. So please pause the video and try to solve this problem. And we will discuss how to do it in just a moment. Okay, so let's take a look at this problem. So we start out with the cannon. It's on top of a hill that is 7.4 meters. Here's our cannon. It's got like a wheel here. It's got like a fuse in the back. And our cannon is going to be firing at an angle 26 degrees above the horizontal. Remember, that means that it's as though you drew a horizontal line coming from this cannon's mouth, and you draw a 26 degree angle above that, okay? So we want to find the x and y components of the velocity and the acceleration at each of these points in time. So basically, we've got our cannon here, and we know that our cannonball is going to come out of here, and it's going to follow a projectile path like this, a curved path towards the ground, and it's going to land somewhere over here. So at every time inside of this problem, we want to be able to look at the velocity and the acceleration of our cannonball. All right, so let's try this. We're going to start off by trying to find out what our initial x and y components are. So at v naught looks like this. Our x component will be this piece of the triangle, the horizontal component of our motion, v naught x. And we're going to have the y component being, I'll do that in green, vertical component v naught y, okay? So now, using trig, we know v naught equals 24, I believe. Yeah, 24 meters a second. Now we can find v naught x and v naught y using trig. Okay, so let's see. Our angle here is 26 degrees. The side that touches the angle gets the cosine. So cosine of 26 degrees times the magnitude of our initial velocity, 24, will give us v naught x. And the side that doesn't touch gets sine. So it'll be sine of 26 degrees times the magnitude of our initial velocity, 24, will give us our initial v naught y. So our initial velocity, we could find this way. Let's go ahead and put that into a calculator. So here, cosine 26 degrees, boop, is about 0.898. I'm going to call that 0.899. Oops, let's do that in blue. 0.899 times 24, which will give us 21.6, thereabouts. So v naught x equals 21.6 meters per second. And then our y component is going to be sine 26 times 24, 26 degrees, sine times 24. Oh, sorry, sine of 26 degrees, by the way, comes out to about 0.44 or 438. 0.438 times 24. So v naught y will come out to be about call it 10.5. Meters per second. Okay, so here we've got our velocity vectors, v naught y and v naught x, excellent. And These are our initial times. So this actually is what the velocity is at t equals 0. And at t equals 0. Okay, so the question asked us to figure out what they're going to be at t equals 0 and at, at t equals 1, 2, 3, 4, 5, and 6. So basically, we're going to be watching this cannonball as it goes through the air, and we're going to examine it at all of these different points in its flight to see what the motion would look like at that exact instant in time. Okay, so in order to figure out how our velocities will be changing, we need to take a look at our acceleration. We know that this is a cannonball. There's no forces acting on it except for gravity, so we're going to have to apply the acceleration of gravity. Gravity, lowercase g, is an acceleration, and it is going to equal 9.8 meters per second squared, and it's going to point straight down. Okay? So, here is the thing. Every second, this g is going to be applying the acceleration of 9.8 meters per second downwards. Okay, so before we move on, it is a good idea for us to establish a coordinate system. I'm going to go with a classic Cartesian coordinate system, so I'm going to call down the negative y direction. I'm going to call up the positive y direction. I'm going to call to the right the positive x direction, and I'm going to call this direction here behind our cannon the negative x direction. So let's go ahead and evaluate what our velocities will be at each time in this problem. So let's say that at t equals 1, will gravity affect my at t equals 1, oh fuck, damn it. Okay, so at t equals 1, will gravity affect v naught x? No, it won't, because gravity is pointing straight down, right? The y component of this gravity vector is all going down. There's no x component for gravity because it points directly downwards. So my velocity in x at t equals 1 is going to just be the same. So at t equals 1, v naught x equals 21.6 meters per second. However, v naught y, or actually, sorry, damn, I'll just start this over. Okay, so let's think about this. So at t equals 1, will my velocity in x be affected by gravity? The answer is actually no, because gravity points straight down. This x component is pointing in the x direction, right? So it's actually entirely unaffected by gravity. Gravity doesn't care about its x position because gravity is pointing straight down. It's got only a y component. So at t equals 1, my x velocity is actually going to be exactly the same. It's 21.6. Another way you could think about this, too, meters per second. Another way you can think about this too is the x component of gravity is 0, right? Gravity's y component is going to be negative 9.8. Gravity's x component is going to be 0 because it's not acting in the x direction. Okay, so over here, now we can see that the initial velocity in the y direction, 10.5, that is going to be affected by gravity. So because gravity is moving in the negative y direction, I can say that my vy at t equals 1 is going to be 10.5 minus 9.8, or 0.7 meters per second. So notice now, this is like up here. This is t equals 1 up here. Notice my y velocity has gotten a lot slower. It's moving upwards a lot slower because gravity is making it accelerate down towards the ground. Okay, let's continue to evaluate. So let's say at t equals 2. Well, my velocity in x isn't being affected by gravity, right? So it's still going to be 21.6 meters per second. My velocity in y, however, remember, every second it's losing 9.8 meters per second squared worth of velocity. Or sorry, 9.8 meters per second worth of velocity. So a second ago it was 0.7. Now it's going to be 0.7 minus 9.8, which is negative 9.1 meters per second. Okay, after 3 seconds at t equals 2, or t equals 3, excuse me, my velocity in x is going to stay the same. Remember, gravity's not acting in the x direction. But my velocity in y is going to be negative 9.1 minus another 9.8 meters per second squared, which is going to be negative 18.9 meters per second. So now it's going down with a higher velocity. Then, at t equals 4, again, my Vx is going to be 21.6 meters per second. My Vy is going to be negative 18.9 minus another 9.8, which will come out to 28 or negative 28.7 meters per second. At t equals 5, our Vx will stay 21.6 meters per second. Our Vy will be negative 28.7 meters per second minus 9.8 equals negative 0.5 meters per second. Okay, and so on and so forth. Now, 38.5 meters per second is pretty fast. At this point, we're actually looking at a situation where our object has already collided with the ground first. So obviously, we said that free fall only will apply for as long as gravity is the only force acting on the object. As soon as it hits the ground, this stops, right? It obviously doesn't keep accelerating and burrowing into the ground because now it's being interacted with by the forces of the ground too. But effectively, what I want you guys to see here is every second we are in the ground, our velocity is getting higher and higher and higher towards the ground. The thing is speeding up more and more and more as a result of gravity accelerating it. So for instance, if I made the hill of this cannonball higher and higher, then this object would have very, very, very high velocity as it hit the ground down here. Because every second it's in the air, gravity is going to keep pulling it down and making that y component of our velocity more and more and more and more and more negative. Okay. So that is how you're going to be able to solve a problem like this. Okay, so as we just saw in the previous example that we did, as we discussed mathematically, you can see that if we have an object that is launched into the air, in terms of its projectile path, the x component of our velocity stays constant because gravity's acceleration is pointing straight down the whole time. As a result, our x components are going to stay the same, they're going to be constant, but our y components are going to change over the course of the object's movement. So you can see that as we go through this arc, the y component of our velocity becomes more and more negative. Here, we start off with a pretty high y component. We have lots of velocity in the y. Gravity slows it down more and more and more until finally up here, the velocity in the y direction is 0. Then, as we start to fall back down, gravity, pointing down still, makes it go faster down, even faster down, even faster down, until we're going very fast down. Down here below the ground, like we saw in the previous problem, it would keep going faster and faster until finally gravity was made to stop pulling on it. So here we can see the logistics of how we're able to get a curved path from this. Because our y component is accelerating, we end up getting a very nice solid projectile curve. And any object that is going to follow a path directed by gravity will follow the same shape. So, something very important to know as we evaluate these shapes is that motion in x and y are fully independent of each other. So if we go back here again, remember our Vx does not care about gravity because it is pointing purely in the y direction. However, our y velocity does. So our velocity in y is affected by gravity, our velocity in x is not. The total velocity of the object is made up of both these components, but my motion in the one direction, in the x for instance, is not affected by my motion in the other. This means that as we do math, we can treat x and y entirely independent of each other, which is really, really awesome. This is awesome because we can now simplify any two-dimensional question into two one-dimensional questions. All we have to do is take any diagonal line and immediately break it into its x and its y component. By doing this, by instantly killing any vector that we see and breaking it into its x and y component, we can treat everything as just straight lines. Because the motion in the two dimensions don't care about the other one, this will allow us to solve problems in two dimensions like solving the same as solving a one-dimensional problem, just once in the x and then once in the y, or vice versa. So this also means that we're going to make separate values for position, velocity, acceleration, basically for any vector measurement. They're going to have a separate value for the x and in the y direction. proof here that I got from the YouTube channel Mythbusters for the Impatient, which is great, actually. It basically shows episodes of Mythbusters that is just the experiment and the explanation. But I've taken a clip from it of a episode of Mythbusters where they actually compared a bullet dropped to a bullet shot out of a gun. So basically, we have two bullets. One is being shot out of a gun at a high velocity and falling to hit the ground like this. The other one has a rig over here that will let it go at the same time this gun fires and have it drop. The Mythbusters did this because they wanted to try to prove this independence of motion, right? This bullet and this bullet, if their Y direction, if their Y velocity only cares about gravity, then they should hit the ground exactly at the same time, no matter what speed in X our gun gave that bullet coming out. So let's go ahead and take a look at this clip and see what happens. I've also sped it up as well, by the way. So you'll end up seeing some high-speed shenanigans here.
Bullet drop versus fire. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. Oh, I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
So we end up seeing here that the difference that comes from the aerodynamics of the bullet, the resistance with the air, the moving bullet that is, comes down to something that's very negligible. 39 milliseconds, 39 thousandths of a second. So basically there is no perceptible difference in the amount of time it took for those two bullets to hit. Therefore proving our theory that the motion of X and Y is independent of the other. Excellent. Okay. So that being said, this means that we are going to be able to split all of our variables into two groups, in the X and in the Y. How we do this is quite simple. All we got to do is put a Y or an X at the end. So acceleration in the X is going to be AX. Acceleration on the Y is going to be AY. That letter we're putting at the end is going to be a subscript, by the way. So A subscript Y, A subscript, to have to be more specific. VFY, final velocity in the Y, VFX, final velocity in the X. V0 Y, initial vertical velocity, or velocity in the Y direction. V0 X, initial velocity in the X direction. Then for our positions, all of our positions we've been using so far in one dimension are X's. We're going to do the same thing for Y, just call them Y's, right? So our initial vertical position will be YI, final vertical position will be YF, and changing Y will be delta Y. Easy. Now, there's one thing that's special about our variables, and that is time. Time is going to be the same for both. Because this time is going to be referring to the amount of time, the period of time, that the object is undergoing free fall. The whole time it's in the air. So, what that means is, if we find the time as a result of one piece of information, we can use that same variable t for the other side, right? So time is the same for both, meaning if we find time from either piece of this, either the x or the y, we can use that same value for time for the other one, because obviously time is not directional, it's a scalar. This also means that we now have two versions of our equations. These are the same kinematic equations you guys have been working with so far. The only difference is that for the x, we put x's at the end, and for the y, we put y's at the end. So exactly the same equations we've been using, just looking at the x versus the y.